Hi folks, in this video we learned two new truth functional connectives, NOR and NAND. NOR is just short for the English expression neither P nor Q. And it's symbolized by this down arrow. So P down arrow Q is true just in case both inputs are false. After all, if I say neither P nor Q is true, when did I say something right? Only if both inputs are false. So that's going to be true on the bottom row, but false otherwise. NAND is just the negation of and it's made up of, it's sort of like the word nor is smushing together not and or. Well, this is just a portmanteau word smushing together not and and. And this is symbolized by a vertical bar, which is called Sheffer stroke because Sheffer studied it 100 years ago. Don't get confused by this bar being the same symbol as the subproofs that we use in formal proofs. Whenever we're dealing with NAND, I will just deal with it in truth tables. I will never ask you to do formal proofs with this symbol. So if you see the vertical bar in formal proofs, it is always going to be signaling subproofs. The truth function for NAND is just the negation of and, so it's false on the top row and true otherwise. If you need a mnemonic device, here's my tip for you. The down arrow, notice the down arrow has this little pointing, the point of the arrow sort of looks like the wedge of a disjunction, the or symbol. And that might help you remember that this truth function has something to do with or. It's the negation of or. And the NAND, the Sheffer stroke, is the other one, the negation of and. The first skill you need to acquire with these is to be able to compute complex truth functions on the basis of them. So here's some examples. If I give you the sentence P down P, or this big complex sentence, could you compute the truth functions of these? So pause your videos now and see if you can do this. Well, this is what you should have done. The first thing, P down P, that's just equivalent to negation. That's false, false, true, true. Now, how did we get that? Because notice my input is the same on both sides. So these are always going to have the same value. When P is true up here, then these are both true on both sides of this thing. And when both inputs are true, the down arrow is false. So that's why there's an F here. And similarly, P is true on row 1, on row 2. So that's why this is true and this is true. And when both inputs are true, down arrow is false. The only time the down arrow is true is if both inputs are false. But that's the case on row 3 and on row 4. So that's why this is the negation of P. Now, once you know that trick, P down P is just not P, you can easily compute P down P or Q down Q. Those are just the negation of the two reference columns. And then I use those values in order to compute the main truth function, this thing in red. For example, the two inputs are false on this row, and so therefore it's true because that's the only time that down arrow is true. Now, once you get this computed, you can see something. The down arrow can express conjunction because that's what this truth function is. And it can also express negation. But remember what you learned previously. Conjunction and negation are truth functionally complete. They alone can express any possible truth function. So if down arrow, if neither nor can express them, then it can express any possible truth function. This is amazing because previously we could only find groups of connectives like not and disjunction or not and conjunction that were truth functionally complete. What we've now learned is that all we need is one connective in order to do all of truth functional logic. So you might ask, why do we have a system like prop, which has 5 different truth functional connectives? Why couldn't we have just had one symbol? Well, it's easy to see why it's useful to have multiple symbols. We created formal languages, formal systems like bool and prop in order to study our reasoning in everyday life. But we don't just reason with neither nor or not and. And so it wouldn't be that helpful of a model in order to do it. It's very cumbersome to reason with one connective. From a logical point of view, it's perfectly kosher. It's perfectly doable. But we're humans. We don't reason like that. I mean, let me just give you one example of how to translate something into just all neither nors. Like, take a sentence as simple as this with 2 of these connectives. If I wanted to use that procedure in order to convert this into all down arrows, the first thing I did was I took the definition of conjunction and I just put that here. And now, in order to get disjunction, I need to duplicate this over with a down arrow as the new main connective. So it becomes this. Now, look at that thing. This is borderline unreadable for me. And that's just this simple thing with 2 atomics and 2 truth functions in it. So as humans, when we're trying to create formal systems that model our reasoning and help us understand when we're reasoning validly or invalidly, one of these logical systems with a single connective is not very useful. But it's really important from a metalogical point of view to understand that technically speaking, we only need one truth functional connective. I mean, that shows how powerful they are. I'll return to that point in a minute. I can't even read this thing, by the way. I mean, in order to say this, I'll take one attempt at it and then I'll give up. But you have to say, I mean, I think I would read this, neither P nor P, nor neither Q nor Q, nor neither P nor P, nor neither Q nor Q. I think I actually got it there. But you probably couldn't even understand me, let alone doing something more complicated. Okay. Let's practice one more before we move on. So you should have acquired the skill of computing truth functions with these things. Pause your videos, even if you didn't get the previous one, and give me the truth function for this. Okay, that was your last chance to pause your videos. If you would like to make this multiple choice, here's some options that you can pick from. The correct answer is one of those. How did I compute this truth function? Well, let me just give you, work it out. Here's my definition again of P down Q. And that's what I did in blue here, because this is just PQ. And so that's why this is FFFT. Now, I know P down P, that's the negation of P. And the next thing I did is I used those two input values in order to compute the main truth function. And that got me TTFF. So this sentence is actually truth functionally equivalent to P. That's the correct answer. Now, if we don't use these symbols in a language, if we're not adding these, we're not going to add these to bool and prop, by the way. We're interested in Sheffer stroke and down arrow from a theoretical point of view, from a metalogic point of view. Why would you care that these connectives alone are truth functionally complete? Well, if you had to manufacture billions of circuits in order to be able to put them together to do any computational task you wanted, it would be really helpful if you could just mass reproduce the same one over and over again. It would keep costs incredibly low and make it very fast. And that's exactly what people did with these integrated circuits. So check out the functional diagram for this Texas Instruments 7400 chip. These little computer chips literally made mass computing possible and changed the world. All you have to do, if you have a whole bunch of these things, is figure out how those logical operations need to hook up in order to build processors, and you can make a computer just using Sheffer stroke or just using down arrow. So here's some of those chips put into a little bit of circuit board, doing some computing. Well, look at this functional diagram. This is the engineering symbol for neither, for NAND, for not and. Because you take a conjunction and then you negate, this is the, if you negate the output, that's putting the negation wide scope out here. Well, these two terminals, these nodes are the inputs, and then this gives you the output signal. So, you know, this is a blank slate. This is just telling us what we want it to do. If you could hook up the wires in this, if you could engineer this thing, then you could have invented the first integrated circuit and you could have changed the world. Well, that's what you have to do now. So this is my next job for you. You're the engineer. You know how to create truth functions in circuits. If you had batteries and light bulbs and some little switches like we've been using previously in the class, I want to see if you can invent this circuit. So pause your videos now if you want to start drawing this thing out. How would you draw it with batteries and light bulbs? If you want a hint, I'll make the problem slightly easier on the next chart. Let me tell you too, that what this is, if you're sort of confused by this diagram, they just put 4 Sheffer stroke gates, 4 NAND gates, all on the same chip. And this is the voltage, and here's your electrical ground. So all of these terminals actually, you have the ability to understand what all of their jobs is. Okay, I'm going to make the task slightly easier for you. I'm going to give you 4 circuits, and you have to tell me which is which. So here's the 4 sentences to choose from. So see if you can interpret these. One of them is that thing that we're trying to create, the thing we want to engineer, the Sheffer stroke diagram. Okay, that was your chance to pause your video. So let's talk about the answers. The first one is just our conditional circuit. And how would you figure that out? I find it really helpful personally to translate these into Boolean form, because my mind reads this in Boolean structure very easily. I can see that it's a wide scope disjunction because there's 2 ways to make this light bulb go on. And I can see also that the P terminal is raised up here, so it's negated. So if not P is the case, then this light bulb will go on. Or if Q is true, this light bulb will go on. So that's why this expresses my P arrow Q. All right, how about the next one? The thing I noticed in the next one, it's also a wide scope disjunction, but both of them are negated because the terminals are raised up here for both of them. And that is actually the same as P stroke Q, because if I have the negation wide scope around this conjunction and I do a De Morgan's law, that's exactly what this is. This is just FTT And that's the NAND that we were looking for. Now it's tricky. This is not super helpful a way to do it if you wanted to actually build that computer chip, because what we need is we need to do it with electromagnets, because that way we can hook them all the outputs up to the ground in the right way, and we can get all the battery lines coming from that voltage line, that one of those terminals. So actually, if you did the thing with electromagnets, it would just look like this. And this literally is what those people, those original engineers, put into those chips in order to make them so powerful. Or if they didn't do it with electromagnets, you know, they found out a different material, like they used silicon or transistors. But structurally speaking, this is what they did in little miniature scale to build that computer chip. Okay, let's go through the rest of the circuits. Number 3, this one, what I notice is these are in series here, one after the other. So this is a wide scope conjunction, and both of them are negated. So the first thing I do is I figure out what this thing is in its Boolean form. And remember, you then just compute this truth function, ft, you know that's not around or, and if you do the De Morgans, you'll see that that's the same as not P and not Q. And then the last one, there's many ways to do biconditional, and I'm sort of cheating because you notice this gate is up, but I sort of flipped it around because this is a very elegant, beautiful solution. This is not the only way to do it, but gets us the biconditional, because remember, this in a sense says P and Q covary in truth value. If they're both true, it's true. So that's when this bit down here. And if they're both false, row 4, it's true. And that's what the position that they're in currently. So there's 2 ways for that to go. What I'm actually modeling is this, wide scope disjunction. Okay, now let's go back to that Sheffer stroke and talk about how you figure that thing out. This is what we said in electromagnets, what that gate would look like. If we took this thing and shrunk it down, we would just put that right here. Now I want to quiz you to see if you actually understand this diagram, because each of these terminals, see, when they make this thing to tell people how to use it, they tell them exactly what each of these terminals does. They tell you which are outputs, which are inputs, where's the voltage coming from, where's the ground going. And I'm asking you, this is number 8 up here. See, this is 1, here's 7, there's 14. Terminal number 8, which of these bits, see, each of these things hooks up to a different terminal. Which one goes to 8? That's what I want to know. Is it A, is it B, C, D, etc.? So pause your videos and see if you can figure that out. Okay, that was your last chance to pause your videos. That is, G is the correct answer, because G is the output. This is going to have current, just in case I've gotten my truth function in the right order to express NAND. And this is the output of that electrical diagram. So these 2 inputs, like this one would be P here, so that would be D. This would be my Q, so that would be C. Now you might be wondering, what do I hook up to these other ones then? What goes to 14 and 7? Well, can you figure it out? I mean, 14, this is the voltage line. So actually what comes from 14 are these ones. All of these then get wired out to 14. And then this stuff is where, or not that one, these ones are where it goes to 7. This is what will get grounded. Oh, yeah, just to show you that, all you have to do, all people did, this was like one of the earliest attempts at fashioning one of these things. And if you can build one of these things, then you can literally just build a computer from scratch. Now, you might not think people really would build it just from one of these, using the same operation over and over again. But this concept of just using Sheffer stroke or down arrow literally changed the course of computing and science and the world. So the Apollo 11 mission, let me give you one explanation. The Apollo 11 mission had a computer that only worked on NOR gates. This whole thing was just built on NOR gates, exactly like that, that Texas Instrument chip was just NAND gates. Well, they had a guidance computer that ran the entire mission, and it was just this thing right here. It was all these NOR gates. If you popped open this box and look inside of it, it looks like this. These are called flat packs. And these little terminals, they're not NAND gates. So the Texas Instrument one was NAND gates. These things are all NOR gates. But if you then pop one of these things open, it looks like this. And all they did was figure out the same engineering problem you did. How can I wire that up so these terminals perform certain logical operations? And then that's just step 1. Once you get this thing so it actually performs the logic that you want, then you need to program the thing so it can land land the lunar module and detach the thing from the rocket. And so after they designed and built this thing, they then coded it in order to run the Apollo 11 mission. And the computing literally did not exist, the computing power or the software in order to run this thing. So the Apollo 11 mission invented that computer just built out of NOR gates. And then this is actually the stack of code that they wrote in order to implement the thing. The director of the program, Margaret Hamilton, is standing here next to it. The thing is as tall as she is. If you want to read about how they did this and how that one guidance computer built around NOR gates landed a man on the moon, there's a fantastic book that you can get a PDF of online. If you look for this title, you can find it. If you want to actually look at the code that's in this 5-foot tall stack of paper, all of it is published on GitHub, and you can check it out. This is a fun little article you can read if you want some more of the background. Now, you might be thinking, though, that's the 1960s. I don't want a time capsule. How is this relevant to what I'm learning about today? Well, let me tell you, this is incredibly relevant to what you are learning about today. I mean, the forefront of science right now is things that have to do with fundamental computing. So quantum computers are literally only finding new innovative physical means of implementing those logical operations that you're learning about in this class. So the most cutting edge stuff are doing right now in science and mathematics and computing has to do with figuring out ways of implementing these very same concepts. So yes, you can't be the first person to invent the 7400 chip, but you can figure out how to do this at a quantum level. Or if you can't do it alone, I mean, I can't do it either alone. You can be part of a team. You can devote thousands of people of the smartest scientists around are devoting their careers to trying to figure this out. You can join those efforts. Don't think this is dead in the 1960s and over and done with. This is still the most some of the most interesting work people are doing. If not quantum computing, how this works in artificial intelligence and computing, or biological computing. So some of the most exciting work being done at UW right now is figuring out how to make cells, tissues, biological materials do logical computations and perform these exact same gates, these operations. So all over the place, from biology to quantum mechanics, it's the same logic. The logic has been with us all along. All people are doing are finding more innovative uses for the same operations. So everything you're learning in this class can be connected to one of these projects at the forefront of science and engineering. Okay, thanks.